Hi there, thanks for joining us. This is Space Nuts. My name is Andrew Dunkley, your host. Welcome along to episode 363. My goodness. Coming up today, we'll be looking at Voyager 2. Well, we won't because it's lost, but it might have been found again. We'll also be looking through the Euclid Telescope. This is an ESA project. It's just found its position in space, and it's nudged James Webb out of the way and said, leave it to me, buddy. And we've talked about this before, I think, a new way of finding asteroids. Well, they've now tested this technology, and it looks like it might have worked, maybe, and plenty more. Plus some questions about satellites crossing the sky, the age of the universe, the ice moons and their oceans, and fate. What is the fate of astronomy, the fate of the universe, the fate of us, the fate of everything? Tom wants to know, and Fred's got the answer. We'll tell you all about it right now on Space Nuts.
15 seconds. Guidance is internal. 10, 9... Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining us to tell all is his good self, Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, how are you doing?
I am well, sir. How are you?
Yes, fine, thanks. All good. Had a good weekend. Had old friends staying with us for the weekend, which was very pleasant.
It's always nice, isn't it?
Yeah, it's good.
Yeah, it's funny. I've got old friends too, and none of them are young anymore. Don't know what happened there.
Either.
Don't know what happened at all.
The sobering thing is they're not as old as me.
Our weekend was interesting because we've sold our house. And
very good. Congratulations.
Thank you. We bought a new one. We move in 6 weeks, so we're packing.
Wow. Okay.
So the place is starting to look like Sydney Airport. There's just stuff everywhere, lying around, sleeping on couches, you name it.
Yes, I know about that. Took us, when we moved last time, it took us best part of 2 months to pack up to go.
We haven't got that long. But
no, you don't. Yeah. That's right.
But we are, because it's a smaller place we're moving into, because we're downsizing. Per the government directive, we've had to offload some furniture, so that goes surprisingly fast when you advertise it on social media. So,
yeah, that's right. It's the way to do it.
It is
Gumtree and all that.
Yeah. Now, Fred, let's get down to business because there's been a bit of a snafu involving Voyager 2, and the spacecraft has been lost, but it may have been found as well. I had to laugh when I read this story yesterday, and it keeps evolving, which I like. I love stories that keep changing and keep updating. But all is not lost because of the way they programmed Voyager 2, which was very good thinking back in the 70s. But
yes.
What exactly happened that caused this in the first place?
It apparently was just a set of commands that is one of these things that's streamed regularly to the spacecraft, saying how you're doing, check this, check that, and that happened, I think, just a few days ago. And one of them, what it did was it said, just move the antenna 2 degrees away from Earth.
Oops.
And that's a bit of a problem because what you've got is a spacecraft with quite a big dish on the Voyager spacecraft. I can't remember the diameter, but it's several meters.
No, I think it's bigger than a dish. It's a wok.
Right. Yes, a parabolic wok. It'd have to be because that's the only way it'll focus. So it's and for those people who are telescope nuts, it's a Cassegrain wok. That's a particular type of telescope that it is. Because it's a radio telescope, we're talking now about the antenna on the spacecraft itself. It's a telescope, basically, that sends and receives radio waves. And it's been pointed slightly away from the Earth. And that's not good because the whole reason for having that is so you can point it at Earth and communicate with the spacecraft. I'd love to know what words were said when they realised that had happened at mission control.
I think the words would have been gosh or darn.
I could be drat as well.
Drat.
Drat's another one, yeah. certainly the one I would use.
Yes.
So this, I should say, this story's got a nicely Australian flavour too, Andrew, because you probably know.
No, it wasn't us. We didn't do this.
We didn't do it, but we are going to come to the rescue.
We might fix it.
Because the Tidbinbilla Deep Space Network down near Canberra, which is part of NASA's Deep Space Network, one of 3 stations there, it's the only one in the southern hemisphere, and that's where Voyager 2 is. So the Tidbinbilla antennas are the only ones that can point to Voyager 2 and send and receive signals. For all the others, the Earth kind of gets in the way. So you can't do it because they're in the northern hemisphere. So yes, all eyes have been on Tidbinbilla. Now, there's a good friend of ours, a good friend of the program, Glenn Nagel. We should get him on sometime, actually. He's the person who deals with outreach, and he's sometimes the director of this facility at Tidbinbilla. But a great, well-known voice on radio here in Australia. And he made the comment yesterday that they'll keep trying. They'll keep on trying to communicate with the spacecraft. But even if that doesn't happen, as you said, because the mission planners back in the 1970s were so clever, every so often the spacecraft resets its parameters and repoints the telescope at Earth. So even though at the moment it's pointing away from Earth, so you can't say, just nudge it 2 degrees to the left. You can't say that. It will happen. That next one will be in October.
Yeah, the 15th, I think.
Yes, that's right. So that in itself is good news, but it's rather a nail-biting wait from the 2nd of August, as we are now, to the 15th of October. So Tidbinbilla have kept trying, and we heard from Glenn this morning. He heard overnight that a carrier wave has been detected from Voyager 2. So that means at least the spacecraft is still working. They picked something up, and hopefully over the next few days, they'll swivel it in the right direction so that it is actually pointing back to Earth again.
Now, 2 degrees doesn't sound like much, but given the distance it is away and the focal range, 2 degrees means it's probably talking to, I don't know, another star.
I should work that out, actually. How many kilometres that is, 2 degrees. If I was fast enough, I could do it in my head, but I'm not. What is it? It's 19, I think it's 20 billion kilometres away.
Wow.
2 degrees at that angle. It's going to be, I think it's going to be millions of kilometres.
Of course, in terms of its signal. Yeah.
It's, there's a comment also from Glenn making the point that here you have a spacecraft that was designed to last 12 years. 46 years later, it's still talking to us. Well, it is when it's pointing the right direction.
Well, it's still talking to us. We're just not listening at the moment.
We're not. Yes, that's right. But what a triumph, for the whole mission planners and the engineers who built it.
And when you consider that the 2 Voyager missions were both kind of backroom patched together thoughts, it was never a designated concept until they realised what a great opportunity it presented.
Yes, that's right.
So it sort of came together over a picnic table, I think, in the back room of NASA. And one bloke went, hang on a minute, it's going to be this convergence. This could be an opportunity.
Yeah, well, you've got Saturn, Jupiter, Saturn, Uranus and Neptune all strung out. So, and Voyager 2, I think it was, certainly visited them all.
Yeah.
Voyager 1, I think it was, just did Jupiter and Saturn. Voyager 1, of course, the most distant human-made object, something like 19 or 20 light hours away, and probably going forever, at least in terms of an object traveling through space. It won't continue to transmit signals forever because its nuclear battery will wear out eventually. But Glenn's comment was, we think we've got at least another decade or so of communications with Voyager 2. And there we go.
Yeah, fantastic. Yeah, we'll hope. I'm glad they found the carrier, and hopefully come October, Voyager 2 will spin itself back into position and go, where the hell are you blokes been? I've been talking to myself for 2 months. I'm going nuts. All right.
3.7 meters, that antenna.
Okay, that's big,
3.7
isn't it?
meters in diameter. Yeah, that's a big piece of kit.
Yeah.
Yes, very impressive.
All right, there'll probably be more on this story. Now let's talk about another telescope. And of course, all eyes and ears and attention has been on James Webb since it got into position and started sending back some magical information and photographs. But now ESA's getting in on the action with the Euclid telescope, which is now also in position. It's not that far away from James Webb, is it? Is it in the same Lagrange point?
Yes, it is. That's right. It's 1.5 or thereabouts million kilometres from our planet, in the direction opposite the Sun, where there's the stable L2 or second Lagrange point, where gravitation and centrifugal force all sort of balance out, and so you've got a null gravitational point. And yes, there's a number of spacecraft there, including Gaia. That's another ESA spacecraft that's measuring accurate star positions. Planck, another ESA spacecraft, which measured the cosmic microwave background radiation. And as you said, James Webb is there too, and they've now been joined by Euclid. You might wonder, actually, why they don't, if they're all at this single point, why they don't collide. And that's because they're not actually sitting at that point, but curiously, they are in orbit around it. And that, I know, sounds daft, that you've got spacecraft in orbit around an imaginary point in space, but it's an imaginary point that's very important because the gravitational nulling effect of these various forces. And so it's possible to have a whole host of spacecraft there actually in orbit around the L2 point, and that's what we've got. Anyway, it was launched 1st of July, reached the L2 point on the 28th of July, so just a few days ago as we're speaking now. And basically its cameras have been switched on and we're seeing the first images, and they are stunning, absolutely stunning.
So I've heard. I haven't actually seen anything yet, but I've read the stories about it reaching its position. What is different about it compared to James Webb?
First of all, yes. So it's much smaller, actually. I think, if I remember rightly, it's a 1.2.
Well, that's only because
telescope.
Everything's bigger in America. But why? What is it?
So it's and it's looking more in the visible region of the spectrum. James Webb is very much in the infrared, and Euclid is in the visible region. Its wavelengths are essentially more or less what's visible to the human eye, from orange up to deep red. But the main difference, Andrew, is it's a wide-angle telescope, and James Webb isn't. That's kind of homing in on the details. It's looking in detail at objects which are, small on the sky, if I can put it that way. Euclid is a wide-field telescope. Look, a lot like the sort of work I used to do with the UK Schmidt telescope at Siding Spring Observatory, which was also a wide-field imaging telescope. And those sorts of things are perfect for doing surveys of the whole sky, where you actually want to record everything over the entire sky. And for the kind of studies that Euclid is aimed to illuminate, if I can put it that way, which I haven't mentioned, it's going to sort out what dark matter is, and it's going to sort out what dark energy is. And to do that, you need the entire sky. You can't just zoom in on one tiny area, which is what the Webb would have to do.
Yeah, it's an exciting project, and I'm looking forward to getting some answers. It's going to take a few months to get calibrated, but I'm just looking at the images now. I just found them on a story on the New Scientist website. It did take infrared photos, but that's part of its testing process. But the normal image that they send through looks just amazing. Gosh, what an impressive array of stars and galaxies, and who knows what else is in there.
Yeah. And so, if I remember rightly from when we covered the launch, Andrew, I think the survey is going to take 6 years. So we'll be on episode
about 700 or 800,
something big. Bigger than that, isn't it?
Oh yeah.
Anyway, Actually, no, we'll be more or less doubling. Yeah, you're right. It'd be about 700, episode 700. Look out for it, folks.
Yeah.
We'll tell you what the...
Well, we'll have the answer to to dark matter and dark energy on episode 700.
Okay.
That's a guarantee.
That's a bit of a... It was Andrew Dunkley who said that, not me.
Well,
I only guarantee Nobel Prizes. I don't guarantee discoveries.
Well, I'm trying for godlike status.
Good.
Because if I'm right.
Well, you've got that. You've got that already. Everybody does.
Dear. No, it's exciting though. With all this technology at our fingertips now, surely we're going to. Well, maybe if we don't get answers, at least we'll get some more information to work with.
We will.
Which will be very exciting. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
3, 2, 1.
Space Nuts.
Now, our next story, Fred, takes us into the realm of near-Earth objects, which we've talked about many times. Of course, the reason we want to pay a lot of attention to these is just in case one pops up and we go, oh, yeah, where's that going? Oh, right, New York. Bummer. So we want to avoid that, and there are systems in place to find them. But one of them is being tested as we speak, and that is the one that uses an algorithm and to find potentially hazardous asteroids, and it looks like it might be working in the early tests anyway.
Yes, that's right. So I think one of the reasons why this work is of importance and interesting, and why are people looking at new algorithms for picking up potentially hazardous asteroids or near-Earth objects generally from image data. And it's because of the fairly imminent commissioning that will happen next year, probably late next year, but it's imminent in astronomical terms, of the Vera C. Ruben Telescope, which is a very wide... we've just been talking about wide-angle telescopes. This is a wide-angle ground-based telescope. But it's in size, it beats the pants off both the Webb and Euclid. 8.4 meters, I think. It's either 8.2 or 8.4, but it is a big telescope, biggest wide-angle telescope ever built. And that's going to be capable of surveying the whole sky I think it's every 3 nights. It can do the whole sky.
Wow.
So one of the things it will definitely see is looking for transient phenomena, and by that you might mean things that come and go. Supernovae, for a start. A supernova, an exploding star, it will pick up probably millions of supernovae. Things like the things that switch on and off, optical pulsars that are blipping in radiation, invisible light, because they're spinning neutron stars. All of that stuff will be picked up, but also lots and lots of asteroids, because they are transient in the sense that they're moving. They're not sort of blinking on and off, except often they're spinning, so they do blink on and off a little bit. But the bottom line is they're moving. Now, if you've got a very deep star field image, so you're looking at an image with often millions of stars on it, then how do you find something that's just moving slowly through these, and especially if it's faint compared with the background stars? And that's going to be an issue facing the astronomers who will use the Vera C. Ruben Telescope for solar system work. It may even be that we'll find Planet 9 that way one day as well. So what has happened is that people have looked at what you can do with AI, of course, what you could do with fancy new algorithms, and the idea is to test the new algorithm, which is completed, and by the way, it's got a name. It is called, if I remember, HelioLink 3D. It is HelioLink 3D. So what they've done, the people who've done this work, I think they're at the University of Washington. Indeed, they are. They are testing it on existing data.
Yeah.
And sure enough, they've come up trumps. They found a potentially hazardous asteroid which was unknown before and had been missed in the current data. It's called 2022 SF289. It won't hit the Earth, at least not in the foreseeable future, but it is potentially hazardous because if its orbit is perturbed at all, then it could hit the Earth. Just to give you the background, I think there are something like 30,000 near-Earth objects known, and about a bit less than 3,000 of those are what are called potentially hazardous, which I think are ones that come within 8 million kilometers of Earth. I think that's the that's the criterion. So they're the ones that everybody keeps an eye on, and naturally we want to know about them because they're the ones we might have to do something about one day. We think that those 2,000 or 3,000 potentially hazardous asteroids that are known are probably about half the total that exist out there.
It's a terrifying thought.
Yes, that's right. So that's why things like this are important. And it actually comes down to changing the algorithm so that you essentially need fewer observations in order to detect an asteroid. I think normally, for example, one of the surveys called Atlas, which is run from the University of Hawaii, they take images of the sky, not the whole sky, but parts of the sky 4 times per night. And those 4 times are basically regarded as sufficient, or the minimum until now. They've been regarded as the minimum that you would need to determine the orbit of an asteroid, a potentially hazardous asteroid. However, the new technique lets you do that with only 2 visits to the same bit of sky per night, which is what the Ruben will do with its, by the way, it is 8.4 meters. I thought it was the mirror size on the Ruben. So yeah, it's an improvement. What it's doing is it's honing our technology in order to match this big new facility, and I'm sure it'll come up trumps, and we'll have an absolute deluge of discoveries of objects of this kind from the Ruben Telescope.
I when I ordered my telescope, I thought I was getting one that big, 8.4 meters, but it was 8.4 centimeters. So I was very disappointed when I unpacked the box. I thought, you can't fit that in there. Anyway.
No, you can't. You couldn't fit it in your house.
No, probably not.
Probably just as well.
Yeah.
What's different about the thing about the Ruben, and it's the same thing we've just been talking about with Euclid, it's its wide angle capability. It has a 3,200 megapixel camera.
Wow.
It's the biggest CCD camera, charge coupled device camera in the world. That's enormous. 3.2 gigapixels of information there. It's extraordinary.
It is rather extraordinary, and it blows my mind to see how fast this kind of technology has advanced. 20 years ago, a digital camera was $1 million, and you could take a really terrible VGA photo with it. Now they cost $2, and you can take the most pristine shots in your backyard or on holidays, and they're just crystal clear. It's just an amazing technology, so affordable these days. And I think I keep saying all the good stuff's going to happen when I'm dead, but it's already started. There's some great technology out there, and I just can't get enough of it.
Yeah, me too. So hang in there.
Hang in. I'm hanging. Yeah, indeed.
So am I. Yeah, that's right. I mean, this technology, charge coupled devices, it originally started as nothing to do with taking images. It was a kind of storage medium on silicon. But it was astronomers, I think, who really drove the development of these things, because they realized that with photographic plates, for every 100 photons that land on the plate, you might record 3 or 4 of them if you're doing well. Whereas with these detectors, for every 100 photons, you could record up to 95 of them. In other words, they're essentially perfect. It took a long time for them to get that way. I mean, the CCDs that I used to use when I was building instruments and doing sort of frontline astronomy, we had efficiencies which were in the 20s, 30s, 40s, and if you're lucky, 50%. But now they're way, way above that, almost perfect.
Yeah.
So as this 3,200 megapixel camera on the Ruben telescope will be.
See, photography could save the world.
It will, yes. Yeah.
And it will certainly be very beneficial in discovery. Wasn't it photography that confirmed the presence of Pluto? Was that done through photographic plates?
It was photographic plates. So, we gave up. So the UK Schmidt Telescope was one of the last big telescopes in the world to keep using photographic plates. And that's because we had the field of view was big enough that the photographic plates were 14 inches square, 356 millimeters.
Yeah.
And CCDs back in those days, back in the early 2000s, typically were about a centimetre square, less than half an inch. So it was the only way of recording data on the telescope, and we kept going pretty well until Kodak said, we're not going to make these anymore. And I think our last plate was taken, would have been about 2003, if I remember rightly, photographic plate.
Yeah, well, technology kind of keeps advancing, doesn't it? So all the old fun stuff tends to vanish into oblivion. In the process of cleaning up the house, I found a bag full of old tapes from my early radio days, and I can't listen to them. It's very hard to find the machinery to play back all those kinds of tapes these days, and I'm talking about even stuff that's more recent, like digital audio tape, which in technological terms lasted 5 minutes because it got overcome by compact disc very quickly. And of course, that's been replaced by hard drive, and it just goes on and on and on. Who knows what's next, Brad? What's the next big thing going to be? You just you don't know.
Well, we've got, we've seen the gravitational wave detectors and all of that sort of stuff. Yeah. That's, again, all on technology. Quantum methods are used in that, and quantum methods will find their way very much into the kind of imaging stories that we do.
Quantum computing, I know they're experimenting with that. I actually heard a story this morning while I was on my way home from my breakfast shift about creating batteries out of concrete house slabs. So you can lay a slab that is also a battery, so you can feed electricity into your slab and power your house. I mean, my word. Where to?
Would you want to be sitting on a battery, though, given what these lithium batteries sometimes do when you overcharge them?
That's a whole new ball game. I don't know how I'd feel about that. The house burnt down. I wonder what caused that.
The battery. Just backtracking for 1 second, Andrew. It's not. We were talking about the march of technology, and that's fantastic, and we applaud that. And I'm still in a job because of the way technology has led us explore the universe. But there's still pleasure for a lot of people in actually going back to earlier technology. So one of my sons uses film in his. Well, he's got my old Pentax camera, actually, my old Pentax 35mm camera. There's a gentleman not very far from you who wants to restore the UK Schmidt Telescope to use photographic plates again.
Wow.
Which is really interesting idea, partly for educational purposes, but also partly because there are some ways in which plates are actually more satisfying, even though you don't get the ultimate sensitivity. They do give you a different view of the heavens. So watch this space, that might.
Yeah. I imagine if I ever went to a school to demonstrate how we used to literally edit tape.
Yeah. With the knife.
With the razor blade and the
razor
editing block. They would just be completely gobsmacked by how weird it is, because it is a strange process.
But it is.
But it's a heck of a lot of fun. Although I've never enjoyed editing much, but there was some satisfaction in doing a perfect edit with a razor blade.
Yeah,
getting it so right that no one knew that there was half a paragraph missing from that statement.
Yeah.
Never let the truth get in the way of a good story. That's because of editing.
Yes, indeed.
You're listening to. Oh, by the way, if you want to chase up that story about the asteroids and how to use the new technology, the algorithm to find them, and the Vera Ruben Telescope, it's on phys.org.
Roger, you're loud and clear here also.
Space Nuts.
Okay, Fred, let's see if we can answer some audience questions. Just looking through them. No, they're all too hard. So that's the end of the show.
Oh, thank goodness.
Yes. Our first one comes from Ralph.
Hello, Master Nuts. This is Ralph in Northern California. 2 questions, one about satellites, the other about the age of the universe. We had an exceptionally clear night when the space station came over recently, and I watched it go across the arctic sky, and I got to thinking, how far has that thing traveled as I'm watching it? On ground distance, is it going hundreds of miles and I can still watch it, or has it traveled thousands of miles and I can still see it in the distance fading away? Has it gone across another state? Just curious how far the distance is on the ground when we're looking at a satellite traveling across the sky. The second thing about that is another satellite came through a kind of a northwest to southeast trajectory, and it was traveling much slower, but it didn't seem to really be higher. I'm wondering, wouldn't height be directly proportional to speed? The other big question is about the age of the universe, and I think it was the Royal Astronomical Society recently came out with a paper stating that they think the universe is twice as old as we thought. So not 13-something billion, but 26-something billion. Wonder if Professor Fred had thoughts around that. Interesting stuff. I guess the galaxies they saw, or the stars they saw, were much more mature than they would have expected to be early in the universe. Looking back. You know what I mean. Thanks for the show. Keep it up. Thanks.
Thank you, Ralph. I'm not surprised we got people asking about the age of the universe revelation, because we did actually discuss it last week. We'll get to that in a minute. But the observation of satellites from the ground and how much ground they're covering while you're watching them cross the sky, it's a good question. I've often wondered that myself.
Yeah, it is. And so, Ralph, great thing to mention. I guess we're talking about thousands of kilometers, actually.
Mm.
So for the International Space Station, which is at about 400 kilometers up, if you think of a simple triangle where it covers 60 degrees of sky, then it's going to cover about 400 kilometers.
Yeah.
Is that right? The equilateral triangle. So just reducing things to the simplest terms. So yeah, you from horizon to horizon, and it's not often we see satellites from horizon to horizon, because usually at some point they drop into the Earth's shadow, and so you don't see them anymore. But they will be covering a matter of thousands of kilometers, so probably not thousands of miles, but maybe 1,000 miles tops. That will be 1,600 kilometers. I think it will be a bit less than that, but and once again, it depends on the height. The International Space Station is what we call low Earth orbit at 400 kilometers. That's fairly typical. Most Starlink satellites are a bit higher than that, up at 500, 550, I think, kilometers. Something like, what's that, 400 miles, 380 miles or something of that sort, thereabouts. So, the higher the satellite, for the same arc that you're following it, it's going to cover more distance, physical distance. Yeah. But yeah, I would say hundreds to thousands of kilometers. So it's a great question.
Yeah, I don't suppose speed would be much of a factor, though, because the height would determine the distance covered. The speed wouldn't really affect that. It would just be going faster or slower, but still covering the same distance.
The speed is absolutely locked into the height.
Yep.
So and that's all about orbital mechanics. So the nearer that you are to the Earth, the faster you're going. And the maximum, which is about 100 kilometers, I think, because below that you just burn up, is just shy of 8 kilometers per second, 7.9 kilometers per second. By the time you get to the geostationary orbits, these are 36,000 kilometers away, the orbital speed is 3 kilometers per second. So you can see that fall off. But for low Earth orbit, they're typically 7-ish kilometers per second. So the height determines the speed. And that's why Ralph's second part of the first part of his question about satellites, the one he saw going from northwest to southeast, he said it's moving more slowly. That just means it's higher, because we're seeing it. it's moving physically more slowly, but the bigger effect is the fact that the angular speed across the sky looks slower because it's further away.
Right.
Basically, it's going at the same speed but further away.
Okay, cool. Now, he's asked about the age of the universe. We did talk about it last week. There's a new theory that it's 26 billion years old versus 13.8 or 13.81 because it's been a week since we spoke about it. Now, he asked for your thoughts. I think you did give them to us last week. You have your doubts?
Yeah, I do. I think it's there's no sort of a killer piece of evidence here. So just reiterating what Ralph says is correct, that with the Webb telescope in particular, we look back in time. We look back to objects 13 billion years distant. 13 billion light years distant in an expanding universe. Excuse me. So we're looking back in time. That's the main thing, 30 billion years. And we're seeing things that look more mature than we expected. We see galaxies that are, have got more structure to them than we would have expected to see, and more of them.
Mm.
And so that's why people have been looking at, well, have we got the whole thing wrong? And it's taken I've forgotten his name. Was it Dr. Gupta, I think?
That sounds right.
It was,
Sounds familiar.
At Harvard, was it? I can't remember. Anyway, no, Toronto. It's University of Toronto. See, my memory does work from time to time. And has developed this theory that goes back to stuff that was being proposed back in the 1960s, what's called tired light, that just because things are traveling through space for a long time, they get tired and lose energy, and that means they look red-shifted. And we interpret the redshift, of course, in the standard cosmology as being purely due to the expansion of the universe. The wavelength is stretched by the expansion. But the tired light, and what Dr. Gupta did was mix the two, threw in normal cosmology with the expanding universe and the tired light phenomenon, and kind of tinkered around with the parameters, made it all work, and got this revised age of the universe of 26. Was it 26.7, something like that, billion years?
Huge number.
Which it would need to provide much more evidence, probably from something like the cosmic microwave background radiation, investigations of that, or maybe down the track from gravitational wave astronomy. But it would need much more evidence before people throw away the standard cosmological model that says that the redshift is due to the expansion of the universe.
It'll get some brains ticking, though, I imagine.
Yeah, absolutely right. Yeah, because as soon as somebody sees a paper like that, they want to have a go at, not demolish it just for spite. They want to understand it, see how it compares with our overall picture. And it's all about body of opinion, really. You know, the scientific evidence stacks up in favor of one thing rather than another. And even though both of those might have problems of some kind, one theory versus another, the better the evidence fits one theory, then the more likely people are to believe it.
Yeah. So watch this space, Ralph, and thanks for your question. Let's move on to our next question. I love this one. This comes from Ryan.
Hey guys, this is Ryan from the great state of Delaware back in the States. I had a real quick question that's kind of bugged me every time that I hear people talk about Enceladus or Europa. I always hear about the subsurface ocean and that it is a saltwater ocean. How do we know it's a saltwater ocean? I thought the salt in our oceans was made from rain falling on land and percolating through rocks and it draining through the rivers into our ocean over the millennia. How does Enceladus and Europa have salt in their ocean? Thanks, guys.
Thank you, Ryan. I think it's the tin can lid that's on the top of Europa, which, you pull the lid back and it's brine. It's a terrible joke. I don't know why that came out. But, how do we know that, or is that what we believe, that they're oceans of salt or something akin to that?
Well, the evidence comes from the spacecraft that have been investigating those.
Picking up samples.
Not samples, no. I mean, you can do that with Enceladus because Cassini flew through the plumes, the ice geyser plumes that come from Enceladus' south pole, And so there was a direct investigation of what was in those plumes. And yeah, there were all kinds of elements and effectively minerals. I don't think the thing was set up to try and detect molecules. I think it was just atoms, although it did detect molecular hydrogen. That's because nobody had a clue when Cassini was being built and sent off on its way. Nobody had a clue that it would fly through the plumes of ice coming out of a subsurface ocean.
Yeah.
So what tells you that these oceans exist are a number of things. You can tell that there's a subsurface global ocean by the fact that the surface features on the ice don't actually match the rotation of the body itself. So that's how we know that Titan has a subsurface ocean, Saturn's moon Titan, because the longitude of the features on the ice changes backwards and forwards. And it's because it's going around in an elliptical orbit. The body of the moon, the rocky part of it, is tidally locked to always face Titan, but the surface, the icy surface, is swiveling backwards and forwards as it goes around.
Yeah.
And that's telling you that there's a liquid connection between them. It's not a solid connection. And that's true with these other moons. So that tells you that there's water there. But something else that tells you that it's water and tells you that it's salty is the magnetic field. It's the magnetism of these worlds and the way it behaves and the way you can sense it at different points. That's what tells you that there is salt in the ice. In the water. Excuse me. Now, where it's come from is probably just leached from minerals within the rocky body of the object, because this is water that's been in contact probably with hot rock. When you've had subsurface, what they call them, submarine vents, hydrothermal vents, which we think are recirculating this water through the body of the rock and up again into the sub-ice ocean. Well, that's probably where the salt is imprinted into the water itself. But yeah, it's fantastic stuff. It's probably more, there's probably other minerals in it as well. It's probably what we would call very hard water. Yeah. Water that's very rich in minerals.
Yeah, well, like the water we have here in Western New South Wales. A lot of it we source is from the river, but we also get it from the Great Artesian Basin, and that's very high in mineral content.
Yes, that's right.
You just look at the shower screen to figure that out.
Yeah, that's right. And the inside of your kettle kind of clogs up with all that stuff. Yeah.
Fascinating.
So that's probably where it comes from. Yeah, but great question.
I love it. Thank you, Ryan. We have one more question from Tom. This is a pretty deep one. Take a breath, Fred, and absorb this.
Hi, this is Tom from Grimsby, Ontario, Canada. I have a question about fate and free will and whether our choices determine our path. Andrew and Fred, you guys have taught me so much about astronomy and space science. Thank you. And today, clearly, there are many unknowns regarding the behavior of the universe and new discoveries happening every day. I can conceive of a time, perhaps millennia from now, when all things about the universe could be known. And by that, I mean every detail of the behavior and journey of a single atom throughout its existence, past and future, might be known, as every step would be governed by definable, well-understood processes. In other words, every detail of the fate of the atom could be known ahead of time. And this might equally be said about every atom in the vast universe. Enter life processes and freedom of choice. Do the atoms in life processes represent a departure from this way of thinking? Or are we kidding ourselves, as we did with the Earth-centered model of the universe years ago? Are life processes the only tiny pinpoint in the vastness of the universe where things that can truly never be predicted happen? Or are they predictable too, and we just can't see it? Thank you again for a great podcast.
Wow, Tom, that's deep. That's as deep as the oceans of Enceladus. That one. You're an optimist. I'll put that in play for the moment. All the answers to the questions of the universe one day may be known. I think that's a big statement. No, look, you might be right. But is it possible one day we will be able to predict the life of a molecule or the life of, of anything and everything in the universe? Is life, is it possible to predict mathematically, I suppose, how things are going to pan out, or is there too much, butterflies flapping their wings and causing cyclones going on?
There's that, but look, certainly the first part of Tom's question goes to the big difference between what you might call, well, I'm not even going to call it that. So the Newtonian view of the universe was that you would be able to, you would eventually be able to label every atom and predict what was going to happen to it. And Einstein liked that view because he liked the idea of precision, and relativity is like that. It offers a precise model of where things will end up because of gravitational interactions and things of that sort. But then along came quantum mechanics, and that all happened more or less the same time as relativity. And Einstein hated it at first because what quantum mechanics said was that you're never going to be able to make these predictions, at least with on an atom-sized scale, because atoms do whatever they want.
Yeah.
And they are bound by these uncertainties. The whole thing, atoms really just reduce to probabilities in quantum theory or subatomic particles. Plus there are mathematical theorems like Gödel's theorem. Gödel's theorem says that we can never have perfect certainty. I think it's Gödel's theorem. I might be getting this wrong, but you can either know the position of an object or you can know its momentum, but you can't know both at some minute level.
Right.
So you can know its velocity or you can know its position, but you can't know both. I think that's Gödel's theory. Anyway, that's Heisenberg. I beg your pardon. That's Heisenberg's uncertainty principle. You've caught me on the hop here. Sorry, Tom.
I like
Heisenberg. Yeah, Heisenberg's principle is that you can know the momentum of a particle or its position, but not both.
Right.
And then Gödel's theorem extends that same sort of thinking into mathematics, and people have then extracted that into, subatomic physics. So there is a very strong body of opinion that we will never be able to predict exactly how the universe is going to behave because of these uncertainties. So, but then if you throw free will into that as well, then you've got an uncertain universe. Now, free will is an interesting concept, and of course, this kind of goes into all kinds of arguments about religious doctrines, Calvinism, and things of that sort that I used to be mixed up with decades and decades ago, because I was very interested in all that stuff. In a sense, relativity suggests that there isn't free will, because relativity suggests that time exists as a whole, that the whole of time actually exists kind of simultaneously, but in some higher dimension perhaps, or in some deeper way than the space and time that we understand. And a lot of contemporary physics tries to build on that, looking for this deeper model of what's happening in the universe. And we hope that one day that something will come out of that, which will tell us what dark matter and dark energy are, because we want to know.
Or could be the Euclid telescope.
Who knows? The Euclid telescope might open some ideas on this sort of stuff. So, Tom, you're right. These are deep questions, and but just have a look at the uncertainty principles and things like that, and you'll find a whole can of worms there about what we know and what we don't know and what we can never know.
The uncertainty principle. Okay, I'm certain he'll do that.
But will he know his momentum and his velocity at the same time?
Exactly.
Dr. Heisenberg says you can't.
Okay, Tom, thank you. We love getting these curveballs occasionally. I love springing them on
No,
Fred.
we don't.
I love springing them on Fred. Thanks for sending it in to us, and keep your questions coming. We always love to hear from you. Go to our website, spacenutspodcast.com, and just click on the AMA link or the Send Us Your Voice Message tab. And if you've got a device with a microphone, such as a smartphone, you can record your message to us. And don't forget to tell us who you are and where you're from. And have a look around on our website while you're there. We doubled our traffic last week. 2 people looked, and I was one of them. I wasn't there long enough, though, so it didn't register.
Didn't register. Yeah, should have left your momentum behind.
I probably did. It seems to be a thing with me. We're all done. Fred, thank you very much.
It's a pleasure. Thank you for having me. Thank you for the curveballs.
I'll keep him coming. Don't you worry about that.
See you next time.
All right. Thanks, Fred. Fred Watson, astronomer at large. And thanks to Hugh in the studio, who didn't say a word for the whole episode, which is refreshing. And from me, Andrew Dunkley, it's been great. As always, hope to join you again, or hope you can join us again on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.